Welcome back to the Explainer. Okay, today we aren't just looking at some random column on the periodic table. No way. We're zooming in on a highly reactive, incredibly dynamic family of elements known as Group 17. I mean, these elements literally shape everything from the water we drink to the chemical reactions that light up our labs, so we absolutely need to understand them. It's time to get up close and personal with the halogen family portrait.
Here's our quick roadmap for today. We're going to start by meeting the halogens, then track the trends in their size and reactivity. After that, we'll watch their displacement battles, put them to the ultimate test with sulfuric acid, and finally, spot them out in everyday life. Let's get into it.
All right, Section 1. Meet the halogens. So who's in the family? We've got fluorine, chlorine, bromine, iodine, and acetine. Now, as you probably know, these are all nonmetals, and at room temp, they exist as diatomic molecules, meaning they're basically always found hanging out in pairs, like Cl2 or Br2. But here's the absolute critical feature that drives their entire personality, honestly. Every single one of these atoms is desperately seeking just one single electron to achieve that perfect, stable, noble gas configuration. This intense craving for one more electron, that's exactly what makes them so famously aggressive and reactive.
Moving right along to Section 2, Trends in Size and Reactivity.
Now, what's really fascinating here is the sheer contrast. Think of fluorine, right at the top of the group, as the super aggressive, compact younger sibling. Because it has the smallest atomic radius, its nucleus has a tremendously strong pull on its outer electrons, giving it the highest electronegativity. But on the flip side, way down the column, we have iodine. It's kind of the sluggish, much larger, older sibling. Its enormous atomic radius means the nucleus is super far away from that outer shell, which results in a much weaker grip on its electrons, meaning it has the lowest electronegativity.
So check out the cause and effect happening here. As we move down the group, the physical atomic radius naturally increases, right? So the atoms hold more electrons. Well, more electrons means more opportunities for temporary imbalances or instantaneous dipoles, which creates a stronger physical stickiness known as van der Waals forces. This increasing physical attraction between the heavier halogens is exactly what drags them from being floating gases at the top of the group down into liquids and finally into solid states at the bottom.
The absolutely crucial takeaway here is that their ability to act as oxidizing agents, essentially their sheer power to bully other elements by stealing their electrons, fades completely as they get physically larger. You see, because they want to gain electrons, halogens naturally act as oxidizing agents. But as their atomic size swells up going down the group, their electron affinity drops off a cliff. The big guys simply don't have the pulling power to snatch electrons away like the smaller, tighter elements do at the top.
Which brings us to Section 3, the displacement battles. In the lab, we get to see this whole bully hierarchy play out in real time through the rule of displacement. Basically, a more reactive halogen can literally displace, or just flat out kick out, a less reactive halogen from a halide solution. Since those smaller halogens at the top of the group have that crazy strong pull for electrons, they'll aggressively force the larger, weaker halogens out of their chemical compounds just to take the electrons for themselves.
Let's actually walk through one of these chemical battles step by step. Imagine you've got a test tube with a totally clear solution of sodium bromide. In step 1, we add some chlorine water. Well, because chlorine is higher up on the periodic table and way more reactive, step 2 happens instantly. The chlorine oxidizes the bromide ions, basically mugging them for their electrons. And in step 3, you see the physical proof. The solution suddenly shifts to this vivid yellowish-brown color. That sensory detail is key here. That color is the newly displaced bromine, forced right out into the open by the stronger chlorine.
And you know, this brilliantly illustrates the whole family hierarchy. I mean, bromine might have just lost its electrons to chlorine, but watch what happens when we mix bromine with an iodide solution. Bromine is smaller and more reactive than iodine, so it readily steps into the bully role here, displacing the iodine and releasing free iodine directly into the solution. There is a strict, undeniable pecking order in this family, and it is based purely on their atomic size.
Now, if you want to clearly identify exactly who won the battle, you dissolve the results in cyclohexane, which is an organic solvent that forms a distinct layer floating on top of the water. If you dissolve these displaced halogens into that upper layer, you get these vivid, beautiful colors. Chlorine glows this very pale green, bromine gens a bright, unmistakable orange, and iodine creates a deep, rich purple. It's honestly the perfect visual test for identifying any mystery halogens in the lab.
All right, Section 4. Testing with sulfuric acid. Before we get to the heavy acid test, here's a quick reference for another really common identification method. When you react halide ions with silver, they form very distinct solid precipitates. Notice the subtle color shift as you move down the group. Silver chloride gives us a stark white precipitate. Silver bromide is a slightly off-white cream, and silver iodide drops down to a pale yellow. It's an elegant, highly memorable way to spot the difference between the siblings right before things get, well, volatile.
Okay, now it's time to turn up the heat. Here is our baseline reaction, dropping concentrated sulfuric acid directly onto solid metal halides to initially produce a hydrogen halide. Now, sulfuric acid is a pretty strong oxidizing agent, and because of the differing sizes and electron holds we just talked about, adding this acid initiates secondary reactions that drastically escalate, and I mean drastically, depending entirely on which halogen you're testing. Watch how this builds.
Starting with the most compact halide, sodium chloride. When we add the sulfuric acid, we produce hydrogen chloride, or HCl gas, and, well, that's kind of where the reaction stops. You see, the little chloride ion is holding onto its electrons so tightly that the sulfuric acid simply isn't a strong enough oxidizing agent to strip them away. So we just see some steamy HCl gas, and that's it. But let's move one step down the family to the larger bromide ion. When we add sulfuric acid to sodium bromide, it first produces HBr. But because the larger bromide has a significantly weaker grip on its electrons, the sulfuric acid easily oxidizes it. The HBr breaks down, and what you observe is super dramatic. A striking reddish-brown, steamy gas of pure bromine forms right before your eyes. The acid totally overpowered the bromide.
By the time we reach the massive iodide at the absolute bottom of the group, things just get absolutely wild. The acid reacts to produce HI, but iodide's grip on its electrons is so incredibly weak that the reaction violently escalates into a massive multi-stage breakdown. It doesn't just stop at iodine gas. It actually reduces the sulfur in the acid so severely that you are left with two shocking observations: visible chunks of yellow solid sulfur and the unmistakable, terrible stench of hydrogen sulfide. Literally, it smells exactly like rotting eggs. It's a perfect, smelly demonstration of how atomic size dramatically dictates reactivity.
Let's wrap things up with Section 5, halogens in everyday life.
Before we look at specific products, we really need to anchor on this fascinating concept, disproportionation. It's a type of redox reaction that's essentially a chemical double life. It is a self-reduction and oxidation reaction where atoms of the exact same element are simultaneously reduced and oxidized. Think about that. In one single reaction, the exact same element acts as both the winner and the loser of electrons. Pretty cool, right?
This exact disproportionation reaction is what happens when chlorine is added to water. It produces highly reactive oxygen atoms, and these reactive atoms, they're completely lethal to bacteria, which makes chlorine an incredible water purifier. Plus, it's the exact same mechanism that makes it such a powerful bleaching agent. Those oxygen atoms literally oxidize and destroy colored dye molecules, wiping out stains. On top of all that, chlorine is heavily relied upon to manufacture PVC plastics and all sorts of industrial solvents.
Meanwhile, the aggressive little sibling at the top, fluorine, has some very unique day-to-day applications. Historically, it was a major player in making chlorofluorocarbons, or CFCs. But today, you interact with it daily as the fluoride in your toothpaste, actively helping keep your teeth strong. And amazingly, this incredibly reactive element is a core part of manufacturing PTFE. You probably know that better as the slick, non-stick coating on your pots and pans that thankfully prevents your morning eggs from sticking.
Of course, we can't forget the larger, heavier siblings down at the bottom of the group, bromine and iodine. Because of how their specific silver halide compounds react when exposed to light, they've historically been the absolute backbone of capturing light and memories in traditional photographic films. So from the very top of the group to the very bottom, this chemical family is deeply, deeply embedded in human technology.
Which brings us to our final thought. Today, we've seen exactly how atomic size and the resulting pull on electrons completely dictate the dramatic behavior of Group 17, all the way from the fierce reactivity of fluorine down to the sluggishness of iodine. So I'll leave you with this question. Knowing these strict cause and effect rules, how might they apply if we were to discover or synthesize an even larger, heavier halogen far beyond astatine?
Like what would its physical state or reactions look like? It's definitely something fascinating to chew on as we look toward the uncharted future of the periodic table. Thanks so much for joining me on this explainer, and keep questioning the elements around you.